All right, and as for today, so we're going to be talking about categorical data. What did we talk about last time? What was the big concept?
About all the, like the tables, data, media mode.
Right, we're still talking about data, but here we have words. What did we have last time?
Quantitative.
Quantitative, right? We had quantitative data, all right, which is all about numbers, all right? Now, be aware that categorical data can be written as numbers, but those numbers will always represent words. So with quantitative data, and we started with that because that's what we're most familiar with: means, medians, modes, all right? Everyone has probably been exposed to that before. Categorical data you've been exposed to as well, but you're probably less familiar of the analysis techniques. And that's what we're going to talk about. So we start with the most famous data that is out there, all right? The Titanic, April 14th, 1912, right? It's going along, woo, cruising speed, drinky, swervy, swervy. Oh my God, all right, there's the 5-second recap of the Titanic. The best part about that is that even back then, over 100 years ago, they were out there collecting data. All right, so they collected lots and lots of data, and we're going to look at two of the biggest data sets, all right, with the Titanic. So they collected some quantitative data, but ideally a lot of it was actually categorical. We had survived category, which they counted as lost or saved or alive and dead. Age, so we had some ages. They also categorized it as adult, and then child. Gender, male, female, and then the biggest one was class: first, second, third, and crew. When you have, and the Titanic had 2,208 people on board. When you have a data set that is 2,000 values long of mostly words, you need a way to organize that data. So what are the 3 rules of statistics? Remember? It's on basically everything we've done.
Make a picture, make a picture, make a picture.
Make a picture, make a picture, make a picture. All right? Because looking at big long lists is not helpful. But what do people love? People love pictures, and that's what we do. All right? We're going to make nice, beautiful pictures. All right? Everything with data analysis. And notice it hasn't mattered what subject we've been looking at, whether it's probability to categorical data analysis, to quantitative data analysis, all right, to normal curves, all right, to regression. Everything we do is about making a picture, all right? Because a picture is worth how many words? 1,000. We do more writing in stats than they do in English, all right? Because we make so many pictures. Our first quote picture is a table, all right? This is the same picture that we had, all right, that we had for probability, because it is just such a nice, simple way to condense information. A frequency table basically identifies the category. And so we're going to look at class. We can pick any category, and we're going to pick a bunch of different ones when we grab the data. All right, first, second, third, crew. And remember, with all tables, we make the totals. All right, so they had the counts out of 2,208, and then we could find the corresponding percentages. And again, all those percentages need to sum to 100%. So we have this very, very simple picture that summarized all those values instead of looking at that big, long list. One of the biggest abuses in statistics is the area principle. And this is the concept of, right? There are 3 types of lies. You guys heard this joke? Lies, damn lies, and statistics. All right? And it's because you can make data do whatever you want. but it's misleading. If I create a picture, all right, and down here I have counts. All right, over here I have crew, and notice I made these nice pretty Titanic pictures. And I dragged the edge, all right, to the corresponding count, which actually is correct. But, all right, this violates the biggest principle of statistics, which is the area principle. There was only 40%, according to our table, of the Titanic was crew. All right, whatever it was, 15% were first and second class, and then this was about 30%. This looks like much more than 40% because of how I've created this picture. Technically, these two should be equal, almost equal to this. But it basically looks like I can fit a bunch of these inside this picture. And that's a violation of the area principle. Now, this is the complex way of doing it, but Excel does this too. And it's basically by when you go into Excel and you hit that beautiful thing that says, turn the graph 3D. If I have a simple pie chart, and let's say this is like 10%, all right, and the rest of this area is 90%. When I go into Excel and I turn the graph 3D and then I do a little bit of movement with the rotation. All right, so that's the shaded region. I can make that 10% look much bigger than 10%. And so our common packages, and this is why I ranted and raved about Excel being a lousy data analysis package, and it's because of simple things like this, that maybe you're not even intentionally misleading, but accidentally misleading. And Excel does this very, very often because everyone's, oh, you know what's better than a 2D graph? Ooh, a pretty 3D graph. And then you can rotate it and turn it and really, really mislead, right? Just accidentally, all right, your consumers. And that is definitely not what we want to do. So the good news, again, we use StatCrunch. And in StatCrunch, our graphs are simple 2D area appropriate pictures. And so we're going to go through how to do this, all right, and the data sets that we use. There are two big ways, all right, that categorical data is displayed. One, all right, is the raw data. Raw data is absolutely fine, and it means you entered a big long list of thousands of values. What is a much more common way is summary data. And actually, we see this very, very often that people just present us with the summary data. So we're going to go look at two different ways of displaying our data. And remember, in StatCrunch, we're going to go to data, data sets. All right, then search by. Well, Corkins. And then category, username. All right, so we're going to look for the Titanic summary data. And mine was on the second page. Actually, while you're there, click the Titanic raw data, just so we can see both. All right, so this is the Titanic raw data. So notice that this is 2,000 values long, and look at all this cool stuff that they collected, right? They had born, they have died, since this is an updated data set, they didn't initially have this, all right? Age, all right, at death, gender, class and department, class, ticket, their fare. We've collected a lot of data since the Titanic actually went down as well. And this is a very big data set. Right? We've got lots and lots of values of this data set. So lost, saved, nationality, all kinds of good stuff. And that's absolutely fine. But a lot of times we're presented with just chunks of data. All right? It's much easier to enter data as summary data And, all right, it limits on what we can analyze, but, all right, we can analyze this quicker as well. All right, so did we get it? All right, so yeah, there's the raw data. Are we good? We got the data? Okay, and we already made the graph, great. Okay, so we're able to pull it all up. Excellent. So in order to create our graph, bar plot with summary, all right? So we're gonna do this both ways. With summary, categories, all right? I just wanna look at class at the moment, counts in count. And then I can hit compute, all right? It gives us our values, and then there are other options too. I can go value ascending, value descending, all right? Lots of options that I can go in here and edit. Frequency, relative frequency of the category, percent. I know about the percent, since we like percent. And again, this shows, right? Crew, 40%, right? We see first class is about 15, second, it's about 13, and that third is just above 30%. So we can make very, very simple pictures. And again, these don't violate the area principle. Similarly, let's go into the Titanic raw data. Graph, bar plot. Now I'm going to go with data. So with data, select my column. And since we're particularly interested in class, I'm going to select class and then hit compute. Oh, and while we're at it, options edit. Frequency, let's do percent here just so we can compare. And it does the same thing. So depending upon the type of data that you have, requires slightly different analysis. All right. Well, basically, we're going to go through making all these graphs and analyzing these both ways. What is much, much better actually than a bar charts are actually overused, is a pie chart. Pie charts are so much nicer because instead of having to select, right, that, change it to frequency and then I compare, right? Pie charts automatically sum it to 100%. And so with my summary data, graph, pie chart with summary, categories, class, counts in count, and I can hit compute. Additionally, I could put titles on these graphs, all right? And I can put titles, change my labels. There we go, we're good. With summary, yeah. Then categories, it's class, counts in count. And so this is what's known as marginal data. What we have here are marginal distributions, right, which we talked about. Marginal, all right? Keyword of marginal is margin. What does margin mean? Not the butter. Where's the margin of your paper? Where is it?
On sides.
Yeah, the edges, all right? So the edges and then distribution, right? Fundamental word is distribute. What does distribute mean?
Spread out.
To spread out, to separate. Now, everyone knows that part of distribute, but the other important part is that when you distribute something, you completely distribute it. And it doesn't matter if I throw some of it out and I keep the rest, it still has to be the total, which means when you distribute 100%. And it doesn't matter if I keep some and then distribute the rest, or I distribute it all. All right, so distribute means that we have to make sure that we sum to 100%, which means, all right, a marginal distribution is the edges that sum to 1. And that's why pie charts are so nice. And again, pretty colors, pretty picture. So that is one-dimensional data. What we look at more in statistics, we saw all those columns, all right? We actually do more multivariate analysis than single-dimensional analysis, but we need We need that marginal distribution. We need information with respect to just one variable so we can compare to multiple variables. One of the best ways to look at multiple variables is a contingency table. A contingency table, all right, identifies two different variables, all right, and we can go to 3 and 4, all right, and at that point, we're basically looking at StatCrunch only. But we can make two-dimensional data, all right, and then it separates, and then we can start looking at conditional probabilities. We use conditional probabilities to test if two different variables, right, are associated or not. And that's one of the biggest things, right? Are two things related? So below, I have this contingency table. I want to find the marginal of survival and the marginal of class. So we just found the marginal of class. Let's go back and let's make the marginal of survival. So graph, pie chart with summary. Now, instead of selecting class, I'm going to select survival, counts and count. And this is what I was talking about. So down here, I could say title. So marginal of survival. And then it puts a nice little title on this as well. And so notice 712, 1496. If we go to our table, back to our table, all right, 712, 1496. The edges, all right, that sum to 1, all right, because it's actually those percentages. 712 divided by 2208, 1496 divided by 2208. And we could do it by hand, but the whole point is that StatCrunch makes this picture, right? No human error, no sketching of graphs, right? It makes nice, clean, concise data for us to view. All right, so marginal distributions, that is definitely something we have talked about and something we're very, very familiar with. We've talked about conditional distributions, all right, but really when we've looked at conditional distributions, we only view them, right? We've only viewed them one value at a time. Now we're going to be able to compare the entire conditional distribution to an entire conditional distribution. So we don't have to compare single value to single value now. And this is the benefit of technology. All right, so I want to go to the Titanic raw data set, and we're going to go tables, contingency with data, row survived, column variable class, and then display a few things. All right, so our Titanic raw data set, stat, tables, contingency with data, since we're in the data, row variable was class, column, or vice versa. Row survived. And then I additionally want to display row, column, and percent of total. This basically gives us everything we could possibly look for. All right, and control click, yeah, shift click, perfect.
What does it mean down below where in the columns where it says chi-square test?
Chi-square, we're going to talk about that later, not today. All right, and we got it. That is absolutely important. And we're going to focus on that another day. We definitely will get to that because that is one of the biggest pieces that we look at. All right, so I have all this value, all these values, and the biggest thing is that this gives me a bunch of conditional probabilities that we looked at before. Specifically, all right, that first value is the row percent. All right, so it says that the first value in each of these squares is the row percentage. That means that is a conditional probability of something given something. Right, so our line represents conditional. So this has something to do, all right, so this described it as lost instead of died. Lost is slightly less morbid, right? So we have, all right, this has to do with first and lost, all right, or survived, however we're gonna call it. And basically it's saying it's 8.22%, but it has something to do with this 123 count that we have here, all right, which is that same value that we saw, all right, in our table right here. So this is still the contingency table, but notice that it presented a bunch of additional numbers for us. StatCrunch did a bunch of calculation for us. We have to understand what that is. So, all right, if that is the row percent, that is saying, all right, given the row, all right, that is given lost, which we're going to call not survived. All right, so this one we're calling not survived. This one we're calling survived or saved, not saved. And then first, second, third crew, they're already labeled as such. So this is saying of those in first class, given, all right, they did not survive. That is 123 out of how many? What number are they using as the denominator here?
0.002.
Not a percentage, it's a total.
Oh,
All right, so we have all these totals, all these values here, right? They did a bunch of percentage calculations, but the rest of it is values we have to calculate. So that's 123 out of what number?
1,496.
Yeah, out of 1496, right? It's given, all right, the row. That's what the conditional is saying. The second value, very similarly, it's saying column percent. All right, so it's still, all right, still has to do with first and not survived. All right, but in this case, all right, this one said first given not survived. What do you think this one says?
First,
Survive. Given 0.
Given survived, we're still in the not survived category. It still has to do with first and not survived, but it's given the column, which means it's flipped. This is actually given the person was in first class. I'm only looking at those that were in first class. Of those that were in first class, who did not survive? 123 out of 324. So it's the same statement, just backwards. The last one, all right, so the last number, and be aware that this is, we're just looking at this one. Every single one of these presented this much information, and StatCrunch calculated it very, very fast. What we have to do is always decode the information. The last value here, it says percent of total, all right? So this has to do, all right, with not surviving in first class, but who is this number out of? So we used the 324 already. We used the 1496. What number is left? Everyone, which is what number?
22.
2208. This one, this last probability, the percent of total, is saying first and did not survive, which is 123 out of 2208. And so it did these calculations. StatCrunch did these calculations for us very, very quickly. And it did it for all, whatever it was, eight of those cells. All right. It calculated 3 numbers each and did all the totals. All right. And all we have to do is understand what those values are. And it tells us, it says, right, the first one is whatever was row, second one is column, third one is of everybody. But basically it did all that calculation, so there is no hand calculation. Everything we're left with is interpretation, which is what modern science is, right? We don't calculate anything by hand, all right? Computers do it all for us. Then we understand what that output is. Now, here's the downside. Okay, so do you know what values to compare? All right, and we could figure this out, all right? But the problem with doing this is it's the same problem as not having enough information. Getting too much information, too many numbers, this just overwhelms people. All right, when you present this, so we can look at this and we can decode it piece by piece. But when you present this, this just like gives people headaches. What's better than a bunch of numbers? A picture. All right, so what we do much more often than that table, and that table has a lot of good info in it, is we create what are known as conditional pie charts. Basically, it's that table, but in picture form, all right? We identify something particular that we're looking for, and we create a conditional pie chart picture, and we can compare the values. Because looking at this, all right? So I have this titled here, all right? This is class given alive, class given dead, all right? That is survived, not survived, all right? So these are conditionals. Now, the best part about this, and this is the same thing, determining, all right, was survival on the Titanic dependent upon the class of the person? For anyone with any semi-knowledge of the Titanic, were those two events associated? Was there a relationship between the class you were in and your survival on the Titanic? Yes, right? We know that from common knowledge. If you know anything about the Titanic, all right, you know, all right, that yes, a higher percentage of people in first class survived than a higher percentage of people in third class. This is our statistical proof of that. And that's what separates statistics from opinion, right? Facts to back up that claim. And here's why the picture is good, and we're going to talk about how to make it in just a minute. You basically look at these two pictures. You say, are these two pictures the same? Do they look the same? No. Basically, pick a color, and the easiest one to pick, I was like, the one that jumps out to me is blue, but it could be any color to you, okay? When I compare blue on this picture, does blue on this picture look the same on these two pictures? No. That means, all right, there is a dependence between class and survival. And that is something people can really get their minds around. The pictures are not the same, hence there was an association. Now, we're going to go a little deeper than that, but that's the general story. That's what you tell to the CEOs, right? Because they just want the basic facts. We're going to go a little bit deeper, all right? And we're going to actually compare our values. And we're going to actually say, okay, if I was in crew, given I survived, that was a 30% chance. Versus if I was in crew, given I died, that was a 45% chance. So probability, crew, given, what we're calling did not survive. I compare that to the probability of crew, given survived. So crew given survived, all right? And the value here is 30%. Crew given did not survive is 45%. All right, and basically here we're comparing blue. And basically this is what you do every time. Pick your favorite color, all right, of the colors presented. All right, pick your favorite color and compare that color in specifics, all right, because we're always about specifics. And basically say, is 30% equal to 45%? No. What is our number for practical independence? What do we say when they're, because again, in real world, no two numbers are actually the same. What is close?
4 to 6%.
4 to 6%. All right, 30 to 45, that's 15%. That is not close. All right, we're gray area, right? We have gray area in statistics because it's not all black and white, but that is different. So the values are different. Hence, survival on the Titanic and the class of the person were dependent events. And that's what we're always looking for. All right. Are these two things related or not? That is the biggest question in basically all of science. We compare two things all the time because the question is always, are they related? All right. And we talked about it, right? When guessing in the dark, or if you pick any two things, are they related or not? What? No?
If you pick them in the dark, you don't know what they are.
Exactly. That's my point. If you pick any two things, most of the time, they are related. More things are related than actually unrelated. All right. This is the whole thing. And that was my analogy, right? This is the thing we've heard all along. Butterfly flaps its wings on one side of the world, tsunami on the other side of the world. Most things are related. When it comes time for your first project, all right, that's what you're going to do. You're going to pick two things, any two things, and see if they're related. Now, makes the most sense if you pick things that you think might be connected, all right? But I've had people who did studies, and they literally did belief in UFOs and eats breakfast. Did those two things end up being related?
Highly unlikely.
Yeah, they did. Because that's the point. It's just amazing. Two random things that you don't think are related end up being related. Why are those two things related?
It's a very good question.
And I have no idea. I was like, he basically ended his study with more research needs to be done. I was like, but that's the whole thing. I was like, when I was in statistical consulting, we did a huge study about cow growth weight. And we had so much data. We had rainfall, slope of the grass, kind of grass planted, hayfield they were in. All right. We found the biggest association between the cow tag ID and their weight. How do they do those cow tag IDs?
Don't they just chip them in then?
Yeah. Randomly.
Oh.
They did that randomly, and that was the biggest association between the cow and its weight. All right. They plugged those into the cows randomly. And that ended up being the highest related factor that we have. So the point is that most things, and I don't know why, things are connected. Now, again, that should give us a warm feeling. I know that, again, right? We talked about this as well. We're always taught that, oh my gosh, I'm an individual, I'm a unicorn, I'm a snowflake. But actually what we are is snow. But that should give us a good feeling because it means that we're connected to everybody, everything you do, no matter even if you think that it doesn't matter, it does. All right? That's actually good news. Okay. All right. So there's my soapbox. All right, back to statistics. So we have two ways to make this. All right, Titanic summary data. This, all right, is actually the more difficult way to actually do a where statement. All right, to do a conditional graph, because we have to use the where statement. The where statement is StatCrunch's way of saying give it. All right, so in our summary data set, so back to our StatCrunch summary data. Oops, which I just lost. graph, pie chart with summary, categories class, counts and count. And I have to use this little build function here. All right, this is StatCrunch's way of saying given. All right, conditioned upon. I want to look at class conditioned upon survival and the two options it has. All right, either survival equals alive or survival dead. Now, important couple of notes. StatCrunch is case sensitive. All right, and if there is a space in your category, because it could be, right? I could have called this dead or lost. Okay, make sure you put it in quotes. So that's just a programming note, right? When using the package. All right, so graph, all right, summary, category class, counts and count, where, all right? So case sensitive, survival equals alive. And again, case sensitive, capital there. And that gives me the conditional graph. All right, Chloe, so we're in the StatCrunch. So it's in your your canvas, yeah. Yeah, your Pearson, exactly.
Yeah, I was looking at it before, like we even had class before,
Okay.
before it even started. But I'll try to get to that.
Okay, yeah. Survival, okay, and go back in and now make survival equals dead. So keep that one and make a new one. No problem. Okay, yeah, beautiful. And this is the condition, okay? So this is just looking at that singular row, all right, back in our contingency table. So that chart we just made actually is only this row, okay? It's only these 712 people that survive. Then when we go back in and we make survival equals dead, it will be only these 1496. We started, all right, with the marginal, which was all 2208. And that's the difference, okay? If you condition upon something, right, we're looking at that happened first. Now, be aware, I can do the conditional the other way. What seems to make more sense when we discuss it would actually be conditioning upon class. Given I was in first class, what's the chance I survive, right? When you actually discuss that, that makes more sense than given I lived, what's the chance I was in first class? But the difference is that when we condition upon the one with less categories, I only have to make 2 graphs. If I condition upon class, how many graphs do I have to make? 4, right? Because I have to condition on each of these. So I get more information with less work, conditioning on the one with less categories, and I still end up with the same result. And we can figure out the interpretation of that just as easily. Given I was in first class, it's more likely I survived than given I was in third class, I survived. Did we get the data set pulled up?
Is that this one?
So, wait, go back to the home. Yeah. So data sets. And then search Bo Corkins, right? So CO, no space, CORKINS. And then switch that to username. Go back here and hit enter. And so this is all the data sets we use. And yeah, we're using Titanic summary data at the moment.
Thank you.
Okay, so, all right, now here's the really good part. In the Titanic raw data set, this is actually what is much, much easier to make graphs because, all right, notice this. All right, in the raw data set, I'm gonna go graph, pie charts with data, not with summary. Columns is class and group by survive. All right, so back to our raw data. Graph, pie chart with data, column class, nowhere statement, group by, survive. And notice, this is the same picture. It looks a little different because the data set is entered slightly differently. But here's the other nice thing. Look at that. It made both pictures for me without having to do anything. When you have the raw data, that's always what you want to do. Unfortunately, in this world, either by laziness or by just a lack of getting the proper information, we end up with summary data a lot. And technically, you could turn summary data into raw data if you're willing to spend however long it takes to enter 2,000 values in 3 or 4 columns. All right. And this is the same thing. All right. Same probabilities. Here's back to crew. So crew is actually yellow on this chart. But, all right, however it made it, it's yellow on both. All right, so we compared blue when we summary data, now it's yellow. Still the same numbers, 45% and 30%. The work we have to go through is significantly less when we have the raw data. All right, but again, it only matters in what we are presented. All right, so the important part, we got to be able to make those graphs so we can compare, all right? But then what conclusions we make, all right? And since we already had the pictures, we were able to make the conclusions there. And this is the biggest one. This is first, foremost, and always, all right? Is there an association or not? Also as a note, and I bring this up mostly just because of Pearson, MyLab, and mastering. You could also make what are known as segmented bar charts, all right, or stacked bar charts, all right? And we can make those, all right, and just so you see them just once. So is that the raw data? All right, so graph, bar plot with data. Column survive. All right, then in grouping options, say stack bars, and then switch this to relative frequency, or actually it's 2%. Oh no, I need within category. Percent within category. So this is another way to display the same thing as the pie charts. Again, here's 45%, here's 30%. The problem is, all right, and actually a lot of data packages do this. What is not here?
Class.
Oh, first class is there. It's blue. How did I know this was 45% and that was 30%?
Oh.
From the other.
From the other chart, all right? Now, can you see that the yellows are different and the blues are different and the reds are a little different and the greens are different, right? Can you see they're different? Which is the main goal, okay? But we always want to go a little bit deeper and I want to compare exactly how they are different, all right? So that's why the pie charts are just a little bit better. All right, that it displays the number. And this is common for a lot of packages, right? A lot of statistical analysis packages, they just don't present the numbers because they know, what are we looking for mainly? Are the pictures the same? No. Are they then associated?
Yes.
Yes. Remember, associated is, and noted, that's a big, I'm glad you did that, Robert, because this is a big thing. We can switch that word. Don't forget the synonyms for dependent. Dependent, associated, related. So I can say the same thing multiple ways and it does confuse us. So we have to know those simple synonyms. Independent, not related, not associated. Okay? And that's what we're looking for most of the time. I want us to go a little further because I think you guys are smarter than most CEOs, right? CEOs, all they ever want is, they're related. Okay, I'm done. I don't need to read anymore. We go farther than that. And so, and so this is my other point. Pearson MyLab Mastering loves to make segmented bar charts, all right? But it doesn't make them from a package, so it actually writes the numbers on them. And basically my point is, it is the same thing, all right? And you'll be able to do the home fun with graphs with the numbers on them. But when we make pictures, we're gonna make primarily conditional pie charts because it presents us with the most information to do the most thorough analysis we can. Okay, then we can answer all kinds of questions, all right? So this is back to our probability. Data and probability overlap heavily, especially categorical data and probability, because I can answer questions all day long, all right, just based on simple charts. Now, every single one of these values was presented in that contingency table with the million numbers. But most of the time, when we look at a question, we're going to be able to see this because we're never going to look at anything with 100 by 100 values. We're going to keep everything relatively, 5 by 5 is about as big as we get. So we can look at it and identify our value just from the simple contingency table. We actually won't need StatCrunch to answer the simplest questions. So what is the probability that a randomly selected passenger survived? So from our contingency table, all right, and remember with tables, the very first thing you do is sum all the totals, but I did that for us. So what is the probability a randomly selected passenger survived?
One out of 20.
711 out of 2,208.
7 what?
Oh, sorry.
712 out of?
2,208.
Yep, right? It's just this whole total, right? Which we already have. 712 out of 2208. And then also remember, with all probabilities, what do we need? Probability statement. Now you can always do this in a sentence. However, probability, and we're calling this S. We already titled it as S for saved, right? Saved, survived, and not survived. What is the probability that a randomly selected passenger was in third class? So what is the probability a randomly selected passenger was in third class?
709 out of 2002.
Yeah, 709. Here is everyone in third class out of 2208. What is the probability that a randomly selected passenger was in third class and survived? All right, I'm gonna make a probability statement on this one before we go get the number. All right, third, what connecting word do I put in here? And, how did you know it was and?
Because you're adding them together.
That's the math, and actually means multiply, right?
Yeah, I guess that's what I meant. You're gonna multiply both of them together.
Actually, no, because we're gonna be able to just look and see what this is. And typically means multiply, right? And only means exactly multiply these if they're independent. All right, we already know, is survival and class independent?
Yeah.
No, right? We just proved that. We just spent an hour proving that, right? Okay, so my question though, how do you know that this was third and survived?
They told us.
In the question, right? It said and. It's not and or, okay? And or are not subtle. There is no subtle way to say those two. What is our subtle? Which one is subtle? Given, right? Conditionals are subtly worded. But and or, it says it straight out. All right? There is no subtle way to, okay, the only subtle way is if you say, but or however, something like that, like a fancy and, okay? But, all right, most of the time, all right, when we're looking for something like this, it straight out says and. Okay, so third and survived. So what is the probability of third and survived?
181.
181 out of everybody. 181 out of 2208. What is the probability that a randomly selected third-class passenger survived? Okay, so this still has to do with third class, this still has to do with survived. But now what? It's a given. Does it say given? All right, subtle. Notice the difference, all right, in what number 3 and number 4 say. What is the probability a randomly selected passenger was in third and survived? What is the probability a randomly selected third-class passenger survived? So again, that's subtle, but we can see the difference. All right, so is this conditioned upon being in third class or conditioned on survival?
Third class.
Third class, how do you know?
Because it's kind of just saying that like they survived, but which one out of the survived people are in third class?
Yes, right? Notice the difference. Randomly selected passenger, that means out of everyone. Randomly selected third class passenger, that means I know the person is third class. Then it's asking, what happened to him? So probability survived given third class, all right? And now I'm all about making the probability statements first and then going and finding the number, right? You can go and find the number and then add the probability statements or a sentence or whatever afterwards, okay? As long as you have both pieces. Now, remember we have a definition for this, but this is one of those ones where I can look at a table and I can just identify this. So survived given third. So given third class means I'm only looking at who? Third class, it means you ignore everyone else. And I only look at this column of third class people. Of those third class people, who survived? Exactly, 181 out of 709. What is the probability that a randomly selected survived passenger was in third class? Now, what happened between 4 and 5?
The given's not directed at having survived.
Yeah, so it's the same thing, but the conditional basically flipped. Be aware, we just saw this in that whole table of all those values, right? That big contingency table with all those percentages. It gave us all these numbers. Feel free to do it either way. You can create that contingency table of values, but again, most of the time, it's good practice to just be able to look, all right, at a simple contingency table without a million values on it and just pull the number out. All right, so third given survived. All right, so given survived means we're out of who?
Out of all of the survived.
Which is how many specifically?
Oh, 712.
Right, it means I'm looking at just this row. So my total is gonna be 712, and then of those 712 people that survived, who was in third class? How many? 181. All right, so number 3, 4, and 5 here. Notice that all of them have 181 in the numerator. What is changing each time? The denominator, okay? Dependent upon the probability statement. So that 181, I can ask that same question, right? 3 different ways, 4 including third or survived, okay? And so basically I can ask that in multiple different ways. So wording is important and it can be subtle, right? If it was up to me, we would always speak like a mathematician. I would always say, if the person had survived, what's the chance they were in third class? That's how every sentence would go. That's unfortunately not our choice. All right, so be careful, all right? English has evolved, it can become subtle. Pay attention to the wording. And last, the devil and not least, did the class the person was on depend on surviving on the Titanic?
Yes.
Yeah. Oh, we just proved that 1,000,000 times. We just went through, right? And proved that. We showed 10 different graphs of how to do it, all right? And then comparing a particular value. That is always going to be a question. So that's always what we're going to focus on with our graphs. Pulling out a number here and there, right? We did all that in like 5 minutes, 5-10 minutes. Proving the two things are associated, all right? That takes the time, that takes the effort. We want to make sure that not only do you compare correctly, and again, I can do 10 different values, right? We compared what we were calling blue. You can pick any of those colors, as well as I can change the conditional, all right? And it's actually a lot faster if we do that in our raw data. All right, we can change the conditional. I can condition upon class and then make 4 pictures. And that's what I'm going to have you do in the activities, because it doesn't matter which one you condition upon. You look at the pictures and you say the pictures, and that's the first instinct, right? The pictures are not the same. They are dependent. They are associated. They are related. All right, or the pictures are the same. And remember, if we actually had it come down to the numbers, nothing is independent, but we have what we call practical independence, that 6% or less, close enough. All right, if they're close enough, we call things practically independent. All right, so, all right, like I said, independence and dependence, that is our biggest thing. That is carried through probability. All right, and now we're looking at how to use pictures to do that. Well, we can do that now mathematically, all right, or graphically. The combination of those is called statistically. So, all right, more examples are always helpful. Let's look at the BAFTA data set, the Bureau of Alcohol, Tobacco, and Firearms. They surveyed 1,530 investigations into illegal gun trafficking over a 2-year period. The study reports the portion of these cases that result in 5 gun trafficking possibilities. All right, so first thing always with our numbers, okay? Whenever you have percentages, especially, all right, what should you check first?
If it's 100%.
Does it sum to 100%? Go ahead and check this real quick for me.
It doesn't, it's above.
It does not, it's above. So the value summed to over 100%. Okay, so that's worrisome. Does anyone know why? So we have gun trafficking violations, straw purchases, okay, unlicensed seller, gun shows, stolen from federally licensed dealers, stolen from residences. All right, this sums to over 100%. I don't know, it's like, looks like 105, 110, like that. Does anyone know why? Why does this sum to over 100%, given this context?
Could one case be multiple?
Excellent. Okay. Multiple crimes. And the problem is when it's overlapping crimes, basically, right? If I go and steal from a federally licensed dealer, am I above stealing from a house? No, right? If I shoot you, right, I'm probably gonna, rifle through your pockets and rob you as well, right? And so it's the concept of a higher crime, and then probably lower crimes were counted. And when they counted, they didn't do the important part of the Venn diagram. They didn't say, 3% include both federally licensed dealers and residences. All right, and this happens a lot. Bad data presentation. When you have data presentation like this, and this happens often, all right, do not make a pie chart, because a pie chart automatically sums it to 100%. The only chart left to make here is a bar chart. And it's really not going to be great because, right, we can't put it on relative frequency because that would then turn those over 100% into percentages. There is no good graph to make here, but the best graph that we could survive making is a bar chart. All right, so BAFTA. BAFTA data. And again, there's not much to the data here, all right? It is summary data, bar chart with summary, categories, case type, counts in percent. And basically there's nothing else to do. Don't mess with anything, right? Because if you change it from frequency to relative frequency or percent, right, like we were doing before, it messes up and makes these numbers that sum to over 100% equal 100%. So there is no good graph, but the least bad graph we can make here is a bar chart. And that's because we can still display the information. And so you can still see that straw purchases is the tallest bar, all right? But these percentages sum to over 100% because we know we have overlapping categories. All right, one other little note of interest. Okay, the study also noted that although corrupt licensed dealers accounted for 133 out of 1,530 investigations, all right, that we were looking at, they were linked to 40,000 out of 84,000 of the firearms involved in those investigations. How does this new information affect what you believe about illegal gun trafficking cases? So remember, we're always writing reports, right? So initially, okay, we're like, okay, the breakdown, it looks like straw purchases, right? Legal gun buyer acting on behalf of an illegal buyer is doing most of the crime. Well, when they involve this, all right, corrupt dealers, 133 out of 1,530, that's less than 10%. So basically we're saying less than 10% of the crime accounts for about what percent of the guns? About 50%. So just like every government agency, they're limited on resources, right? And our goal, right, as people who analyze data is to tell them something. So basically, what are you going to tell them, all right, since they have limited resources about corrupt licensed dealers?
It's still a prevalent issue.
That they're important.
Yeah, even though that's a small percentage of them.
And actually, that's good news. 10% of the cases result in half the guns. Since they're a government agency, they're probably limited on resources. And we want to say, hey, if you solve these 10% of cases, that's equal to solving the other 90% of cases. All right. And that's all. And basically that's what I'm trying to say is we always just want to make sure that when you look at numbers, and people throw out numbers all the time, that you can put it into common terms. So you tell, right, BAFTA, hey, focus on corrupt licensed dealers, because if you solve those 10% of cases, or near 10%, all right, you account for 50% of the guns. And it's always about writing that summary, all right, making sure that you can identify that type of information. All right, another example. Example is always helpful. So the following table summarizes results from 985 pedestrian deaths that were caused by accidents based on data from the National Highway Traffic Safety Administration or the NHTSA. The data set is located in StatCrunch pedestrian deaths. All right, so we have our table, and in this one, we start to finish, we want to look at this information. When we have a table, all right, so I see pedestrians intoxicated, yes, no. Drivers intoxicated, yes, no. I have a bunch of questions to answer. What is the first thing I need to do? looking at that table? Totals, all right, totals, all right, first, foremost, always get those totals down, all right? StatCrunch can do all that for us, it's not difficult, all right, but we want to make sure that we get our numbers, all right? So we have totals, and then our value at the end is the overall total. And then, all right, so individual, right, column totals, row totals. Then remember that the row totals, all right, 325 plus 660 makes the overall total, and that should match up with this number. So always double check that this number and this number, they both sum the same value here. And we already knew what that number was, 985, because it was told to us. All right, so we knew we had 985 data values. All right, so again, quick little checks just to make sure that we don't make a super easy mistake like adding. All right, we have much more complicated things. Find the marginal distribution of driver intoxicated. Marginal distribution. What does that mean again?
The distribution fields
Uh, distribution of, say the last part again?
the
You said it correctly. I thought.
distribution of the outside.
Of the outside, of the edges. Okay, so driver intoxicated, where is the edge there? What edge is that? I only have two. It's this edge. Okay, and remember that the distribution part sums to 100%. Sums to 100%. Okay, so it's not just the yes category, it's both of them. All right, there are two options of driver intoxicated. The driver is intoxicated or the driver is not intoxicated. Which also brings up the next piece of notation. We never use yes or no, because notice both of these are yes or no. So when I have a question and, you know, if it's looking for driver intoxicated and pedestrian intoxicated, I don't want that to say yes and yes, right? Not helpful. So driver intoxicated, and then what's our notation for not intoxicated?
Line on the
The
top.
line on top, right? DI and not DI. And here I'm going to do PI and not PI. So we want good notation. All right, so we can clarify what we're looking for. If you hate the notation, what can you do?
Write a whole sentence.
Write a sentence. Is that better?
Yeah.
Yes, way better. We make the notation to be quicker. A sentence is way better, but we already do a lot of writing in here. We really do. All right, and we haven't even got to the really heavy interpretation stuff yet. So the shorthand is there to help us, okay? But if you're going to use the shorthand, you have to use it correctly. All right, otherwise write a sentence. That actually is the better way. All right, marginal distribution of driver intoxicated. So that is the edge. DI and not DI. And we have our totals, 138 and 847. But remember, it has to sum to 1. So how do I turn those totals into percentages? Or probabilities? I need it to sum to 1. It currently sums to what?
985.
Sums to 985. How do I turn those values into probabilities? Divide by the overall total. All right, I could leave them as such, and typically I would, but I have a feeling we're going to need those values. So I'm going to turn them into their corresponding probabilities. And we're gonna do this graphically with StatCrunch in a bit too, because we're getting to a problem that I have a feeling I'm gonna use it. But we have some probabilities that we can find first. Find the probability that the pedestrian was intoxicated and the driver was intoxicated. So let's start with the probability statement. I'll do the hard part.
PI and DI.
PI and DI. Once again, all right, pedestrian intoxicated and driver was intoxicated. PI and DI. And what is that number? 59 out of
985?
985, right? Probability doesn't specify a particular type, just pedestrian was intoxicated. 59 out of 985. Find the probability that the pedestrian was intoxicated or the driver was intoxicated. So finally, we actually haven't seen one in a while. We've seen a bunch before. All right. PI, DI, what connecting word? Or, again, very straightforward there. What is less straightforward? So PI or DI. All right. Who are those people? So the pedestrian is intoxicated or the driver is intoxicated. And remember, all right, or is inclusive. So it actually means pedestrian is intoxicated or the driver is intoxicated or both were intoxicated.
You do opposite?
Opposite is one way. I was like definitely, so what's the opposite of neither the pedestrian nor the driver is intoxicated? Who are those people? What number now specifically?
581.
The 581, yeah. All right, it's like 581 in order to be a probability, 581 out of 985. And that is absolutely a fast way to do that. That is not the only way, right? That absolutely is probably the fastest way, right? But let's say we didn't see that, and I'm very impressed. Good job, Chloe. All right, okay. So, or typically means what? What does it mean? Subtract is just a fancy add with a negative. So, or actually means add, right? That's the direct translation of language to math. So PI, who are the people where the pedestrian is intoxicated? How many of those are there? 325.
Would it be adding just the 138 and the 325?
Almost. All right. So absolutely. All right. That's where I was going next. So pedestrian is intoxicated 325, driver's intoxicated 138. Probability of PI plus the probability of DI. So 325 out of 985 plus 138 out of 985. Or means add, all right? And you already said it, Robert, but you can also subtract because subtracting is just adding negatives. And this is the problem with the BAFTA data set we just saw. There was things that were overlapping, they were double counting. In this 325 and that 138, did I double count anything?
The fact that they both are.
The both. How many boths were there? 59, all right? So in that 329, I have 59. In that 138, I have that 59. So it actually got counted twice. So I have to subtract it out once. And of course, if we do that calculation, we get the same thing. So either of those are absolutely appropriate. This is the second way that I showed us how most people think about it, because that's kind of the step process of what or means, right? However, highly encouraged, love that you thought of that, Chloe. I was like, that's the way that you think of it the fastest, absolutely. That's kind of the second level, like this is how we typically think about it, because we know or means add, and then we kind of go through the process, all right? But absolutely, whatever is fastest for you. All right, let's look at another one. Assuming the pedestrian was intoxicated, find the probability that the driver was intoxicated. It's a given. This one actually finally has kind of a subtle word. What's a subtle word in this statement for given? Assuming that's basically if then, all right? Finally in the form of if then. If the pedestrian was intoxicated, then the driver was intoxicated. Given, I forgot what it said. Given pedestrian intoxicated. All right, so given the pedestrian is intoxicated, find the probability the driver is intoxicated. And again, I could use the formula that we have, the definition, but with a table, it's just so nice. All right, so given the pedestrian is intoxicated, who are those people?
59.
I'm just doing given the pedestrian is intoxicated. Right. So, yeah, and you were already on the next step, right? So there are 325 possibilities, right, where the pedestrian is intoxicated. Where is the driver intoxicated of those 325? 59. And again, I slow that down, but I was like, already you're kind of thinking faster, right?
I didn't even mean to, I was actually kind of confused about it.
Right, so I'm slowing it down, but if you can automatically just go, oh, it's 59 out of 325, and that's what you were doing too, Bella, right? So that's absolutely fine, right? If you're messing those up, slow it down and do it piece by piece. But I mean, a lot of people just look at it and go, yeah, it's 59 out of 325 done. All right, and then the most important question. Are the events driver intoxicated and pedestrian intoxicated independent? All right, so we can do this by hand, and we've done that a little bit. But what's way better than doing this by hand? What are the 3 rules of statistics? Make a picture. StatCrunch is going to be very, very helpful. Okay, so let's look at pedestrian deaths. Data set. There's. All right, and notice, all right, we see our data. Our data is entered as summary data, which again is very, very common. We want to make conditional charts. So pie chart with summary. All right, and this one, it wasn't given to us. So categories, what?
Pedestrians intoxicated.
Pedestrian intoxicated. Here's the big thing. Does it matter? No. Are we going to use both of those? Yes. So Alright, and they both have two categories, okay, so neither is better, right? What we were talking about before, oh, pick the one with less. They both have exactly two categories, so doesn't matter there. Here's the other nice thing. There is one thing nice about summary data. Counts in. Count. There's only one option. Okay, and then we need to make the where statement. Okay, the where statement is the StatCrunch's way of saying given. So if I had pedestrian intoxicated here, what goes here?
Driver intoxicated.
The other one, okay? And it doesn't matter. I could do driver intoxicated here and then pedestrian intoxicated here, right? You just always have to make sure you're crisscrossing, okay? Now, actually, I need to go back and we need to make sure that, all right? It is case sensitive, all right, so I do want that one because I can spell driver better than pedestrian. All right, driver intoxicated equals yes or no case sensitive. All right, and this is what I was talking about. It's kind of a little programming thing. When you have multiple words, put them in quotes.
Is that an equal sign?
Equals, yes. So. And this is a very, very common thing, whether you're doing Excel, Google Docs, all right? Putting, when you make miniature equations, putting them in quotes, identifying the variable title is very, very common, all right, type of a process. And it's not like StatCrunch specific at all, all right? StatCrunch is a very general language, right, that follows the patterns of every programming language in the last 30 plus years, all right? And then make sure we're case sensitive. And we hit compute. We have that one, but I need two of them. So go back, do the whole thing. And unfortunately, because I'm on the iPad, I can only see one at a time. And then exact same process. Do yes, do no. Computers are nice because then you line them up and you can put them right next to each other. Oh, there is one other thing in options. So if you really hate the normal colors, go down to basic color 7 and pick your favorite color. So you can go to, yeah, orangey, whatever it's called, orangey scale. Orange, oh, it's called orange scale. It used to be orangey.
What's the second one we're supposed to do?
So the same thing, summary, yeah. And then this,
This one, right?
exactly, yeah.
Okay, oh, I
Yep.
did have it right.
Yep. And then, yeah, line those up. Oh, and if you change this color, make sure you change this color, so that way you're still comparing brown to brown and beige, beige to beige.
Okay.
Definitely, because in this case, now you're comparing beige to blue, right?
Mhm.
So to keep it consistent, as long as you change, so you go back in and do options edit on this one. Right, and you can change your color right there. So whatever color scheme you pick, as long as you're consistent. So if you really hate the reds, the primary colors, and you change them both. I'm sorry,
I'm just.
let's look at backwards and talking. Okay, and so you make, no, hold on, what happened here?
Yeah, we're worried about that too.
Oh, you're in with data, so cancel out of here. So you need to go with summary. Yeah. Yeah, so pedestrian there. Then categories count, and then on that one, yeah, see, there you go. Yeah, and now hit compute. Yeah, see, much better. Now repeat that for yes. Oh, yeah, so you changed it to, what color scheme is that? I love that color.
Soft.
Soft, yeah, soft, I like that color scheme. For, yeah, I guess soft, for obvious reasons, because it's easier. Okay, so we have our values. So looking at those two pictures, and again, I can only look at one at a time. So looking at those two pictures, are they the same? Did everyone get them up? Oh, you're good.
Okay, excellent, right, yep, I'm gonna go, compute, okay, drag it over, have those two next to each other. Okay, drag that over, okay, excellent, those two are next to each other. Okay,
All right, so looking at those two pictures, are they the same?
No.
No. All right, and then, all right, according to this one, we have blue and red. Okay, so it doesn't really matter which one you pick. All right, so let's compare the reds. All right, so my color is red. All right, so I'm gonna compare pedestrian intoxicated given driver is not intoxicated to pedestrian intoxicated given driver is intoxicated. So general overview, we can see they are not the same. So pedestrian intoxicated given driver intoxicated compared to, and calling that was reds. Compare the reds. So we're comparing basically those two colors, and again, whatever, it doesn't matter, whatever soft color or orangey or whatever you changed it to. Okay, so give me it was the pedestrian counter, so it was the bottom number. Could be bottom numbers.
Oh.
Okay, so yes, okay, yes is 4275. 2.75. And then give me the other one.
1.4.
31.4. All right, is 43% equal to 31%?
No.
No. And we saw that from the picture. All right, if those pictures look close-ish, all right, then, all right, we have an idea. This then further confirms, all right? Let's see, 43, 31, 12% away. All right, again, not close enough to our values, 6% or less, all right, to be that gray area of close enough. The values are different. So all right, so pedestrian intoxication and driver intoxication regarding pedestrian deaths. All right, probably should have said regarding pedestrian deaths, driver intoxication, pedestrian, but it's good. All right, so they are what?
Not related, dependent, independent,
Those are the options.
independent.
It's independent, the values are different, the pictures are different.
Am I backwards?
Yes.
Okay,
Well, you actually said them both. You said they are dependent, not related, independent.
hold on, I wrote it down.
And that is exactly my point, all right? It does mess with everyone, okay? Dependent, different, all right? Independent, they're the same. Sorry, I don't know a synonym for, that starts with I that means equal. So, all right, the values are different. That means dependent, which is also related, associated, right? All those mean the same thing. And questions are asked, again, in all those variations, are they associated? Okay, again, if it was up to me, the math person, we would always say independent, dependent. English keeps evolving, and so we have to keep up with those very commonly used type synonyms. But that messes everyone up, all right? So don't feel alone there. All right, AKA associated. They are associated, they are related. Okay. 3 categorical variables we will do next time. As for today, guess what fun you guys get to do?
Activity.
Activity time.
Yeah.
All right, data activity 2. Now, on these problems, I basically say you don't have to print any graphs. We have lots of StatCrunch because part of this is being able to operate StatCrunch to know I need to make this graph for this. So on this activity, I have a lot of questions that say, produce a marginal graph, and then I have the picture. Did your graph look like this? Okay, because I want to make sure that you can actually operate the technology. Now, be aware, do you have to use StatCrunch? Can you do these by hand? Yeah. Do you want to?
No.
No, we have the technology, which means, right, most of modern mathematics, most of modern science is you have to operate the technology because it takes a ton of work away from you. Learning to operate the technology is much, much shorter than making all this stuff by hand. All right, so learn to operate the technology, and then we have questions, and then again, all right, we have conditional plots. All right, making the conditional graphs is the trickiest part, especially with summary data, which is our most common type of data that occurs. With summary data, making conditional plots, you have to use the where statement, and that is the trickiest part. All right, make asterisks, highlights, or notes. All right, within your like on your cheat sheet and stuff. Where statement, where statement, where statement. All right, guys, go ahead and do what you have to do. I'm happy to help, but otherwise.